Kia ora Year 12. This video is going to go through how we can use a normal distribution to approximate a Poisson distribution, and it goes with textbook chapter 9D, and there are quite a few examples in that exercise where you're going to need to use this skill. So in this video I'm going to look at when it's useful to do this and when we can do it and how we do it. And then at the end, after an example, I'm going to give you a quick summary with some notes to take down. So please watch the whole thing. I'm going to go fairly quickly. If you think about the normal distribution, it's very easy to use, right? We've got a normal distribution here. We've got a mean of mu and a variance of sigma squared. And so if we want to be able to use that instead of a Poisson distribution, the most obvious thing that we have to have is a Poisson distribution that is symmetric. And when we'd want to do this is if the Poisson calculation was really painful. For example, if we had to add up 100 different probabilities. So in that case, finding the area under a curve using a table is going to be way easier than adding up lots of probabilities. Now, as you know, in real life now, you'd probably be doing this with a stats package or a spreadsheet. But it's still a nice skill to be able to think about when we can use one distribution instead of another. And more practically, it turns up in the A-level exam very, very often. So let's look at what the Poisson distribution looks like. Well, this is one case. This is where we've got a lambda of 0.8, right? So forget that it's called mu. That's just what the computer package spat out. But so the mean here is 0.8, and you can see that it's incredibly asymmetric. So we definitely wouldn't be able to use a normal approximation here. This is what happens as we start to have lambda moving up. So even by the time we move up to an average rate of 1.8, you can see that this is starting to get more symmetric, but still extremely asymmetric. By the time we get to a lambda of 7, you're getting quite a symmetric shape coming, but you can see we've still got trouble, right? Because it's truncated at 0. It can't go below 0. But there's not much probability down here anyway. But it's still not that even. So at lambda of 7, we don't want to be using a normal approximation. The magic number for our purposes is lambda is 15. This is what it looks like here. So you can see you've got a histogram where it looks pretty good, right? So just looking at each side here, you can see these two match up. Here it's matching up. It's pretty good here. It's going a little bit off, but it's good enough to model something. So our rule is when lambda is 15, we can use the normal approximation. But what you have to remember is that we're working with a bar chart, right? So we've got x, which is normal, and x dash, which is what I always call my Poisson approximation. Sorry, x is not normal, wrong way around. X is the actual distribution. X is Poisson, and it's got a mean of lambda, and it's got a variance of lambda. And x dash will be roughly normal, and the mean that we'll use will be lambda, and the variance that we'll use will also be lambda. Okay, but because we're working with approximating a discrete thing with a continuous thing, we have to do a continuity correction. And the way to do that is to think about which bar do you want to have included. For example, if you want to have the probability that x here is greater than 20, that means that you want to have this bar included, the one that I'm colouring in, at 21, but you don't want the one at 20. So when you do your correction, you're going to use x dash greater than, and think about the edge of that bar, so it's going to be greater than 20.5. And when I'm doing these problems, I always draw a rough sketch of just the 3 bars that I want in, so that I don't go wrong with that, because it can make quite a difference depending on where you are in the shape. And then the last one I want to show you is when lambda is 100, that it looks very, very close to a normal distribution. So the example I've done here is about people going to the local dairy, and it's very simplistic. We assume that in 1 hour, 10 people come in, and we naively are going to assume that the average rate of 10 people per hour coming into the dairy is constant, and that people arrive randomly and independently, because we're just doing a maths problem. So that means that we have got a Poisson problem. So lambda is equal to 10 per hour. But I've asked you in a 12-hour day, find the probability that 140 or more people come to the dairy. So we need to, first of all, to do the thing we did back in exercise 9A or B, and change that lambda to match the time period. So in 12 hours, we're going to have a lambda of 120. So we're timesing that by 12. Now what I'm working with is x is distributed as Poisson, and it's got lambda of 120. We want to find the probability that x is greater than or equal to 140. So that means that on my bar chart, I want to include the 140th bar. And the limit of that bar, and then I want all of these ones up here as well, starts at 139.5. So that means that I'm going to be finding a normal approximation at 139.5 or up. And I can write that as a weak or a strict inequality. It doesn't matter because now I'm finding the area under the curve, and I'm finding it from 139.5. Okay, so x is my Poisson distribution, and x bar is roughly normal with a mean of 120 and a variance of 120. Okay, so that's what we're going to work with from here on. And so now I'm back to doing what I did in AS, right? I just want to find the probability that x bar is greater than 139.5. So we standardize and we get the probability that z is greater than 139.5 minus 120 divided by root 120. That works out to be, well, when I did that, I got z greater than 1.780. So we're looking to colour in, whoops, turn that off, hang on. We're looking to colour in that bit of the normal distribution. So it's going to be 1 minus phi of 1.78, which gives me 0.0375. So I'll show you where that's coming from. Here's my normal distribution table. I've got 1.78, which is here, and the number is 0.9625. Okay, so now for the quick summary and some notes for you. We've got to be working with a symmetric Poisson distribution, so we need to have mu equals 15 or higher. So I've said mu there, I mean lambda, so lambda has to be 15 or higher. We're approximating a bar chart, so we have to use this diagram here to figure out what continuity correction we want. And we're going to use lambda for both mu, and we're going to use lambda for sigma squared. Okay, thanks for watching. Make sure you do plenty of examples of these. There are tons of them in the exercise 9D.